Hi,
You
Lee.
do very well.
Great.
Bingo.
Thank you. We're all set.
It's all yours.
Hi, everybody. Welcome to a virtual GAAC tonight. Our speaker tonight is Kevin Luhman. He got his undergraduate degrees in astronomy and physics from the University of Texas and earned his PhD in astronomy at University of Arizona and is now a professor of astronomy and astrophysics at Pennsylvania State University. And he has done a lot of work looking for and finding brown dwarfs. And I assume that's what he'll be talking to us about tonight. Thank you for coming and welcome, Kevin.
Thanks. So during this discussion, please feel free to ask any questions that you have along the way in the chat window. So tonight I'm going to tell you about some of my recent work searching for brown dwarfs at very small masses. So as many of you may know already, stars exist for a wide range of masses. There are some stars that have smaller masses than the sun, and some that have larger masses. Now, if you were to imagine that you were sitting at the center of a more massive star, because there would be more stuff sitting on top of you, you would experience a greater pressure. So that means that higher mass stars have higher pressures. Now, pressure and temperature go hand in hand. If one is high, the other one is high as well. So higher mass stars, because they have higher pressures inside of them, they're also hotter. So the idea is that higher mass stars are hotter, lower mass stars are cooler. Now, meanwhile, there's a certain minimum temperature needed inside a star to fuse hydrogen. And that temperature is about 10 million Kelvin. But given that stars that are smaller in mass are cooler, in theory, there might be some stars that are born with such a small mass that they never reach the minimum temperature of 10 million Kelvin to fuse hydrogen. And that's what a brown dwarf is. So a brown dwarf is a star that was born with a mass too small for it to be hot enough to fuse hydrogen. And the mass dividing line between stars and brown dwarfs is about 8% the mass of the sun, which corresponds to about 80 times the mass of Jupiter. Now, because brown dwarfs don't fuse hydrogen, they don't have an energy source, and so they get steadily cooler and fainter like a dying ember over time. And so a big question that I've been trying to answer for many years is, what's the lowest mass at which brown dwarfs exist? Well, to try to answer that question, we need to first think about where is the best location for searching for the least massive brown dwarfs. And the answer to that question relates to how brown dwarfs are born. So both brown dwarfs and stars are born from the collapse, gravitational collapse of huge clouds of gas and dust in space. An example of one of these clouds is shown on the left. And then over a period of about 1 million years, gravity causes the cloud to collapse and coalesce into a spherical object that we see as a star. Now, as mentioned on the slide here at the bottom, this comparison between a cloud of gas and dust and a star, it's not to scale. So a star like our sun is about 10 million times smaller in diameter than one of these clouds, which is like a light year across. Now, in that process of a cloud of gas and dust collapsing to make a star, there's a lot of gravitational energy that's converted into heat. And so as a result, when a star or a brown dwarf is born, it's pretty warm and pretty luminous. And that's going to be illustrated in this diagram here. So this is a diagram of what's called luminosity on the vertical axis. That's the total energy output, the total amount of light produced by a star or a brown dwarf. And here we're showing it in units of the luminosity of the sun. So the top of the axis is 1. So that refers to the sun's luminosity. That's what the sun is up here. And then the horizontal axis is the surface temperature of a star or a brown dwarf. Now, models for how stars are born, they predict that a star with a mass of 10% the mass of the sun, that's like the least massive star, when it's born, it should have a temperature and a luminosity near this black point. But then after the star is born, it collapses for a while. And because it's shrinking, its surface area is decreasing, which makes it fainter. And so over about 100 million years, it shrinks and it gets somewhat fainter. But eventually, as it shrinks, the interior is experiencing increasing pressure, therefore an increasing temperature. And eventually, as it shrinks, it gets hot enough to fuse hydrogen. And that fusion provides a source of energy that halts the collapse and stabilizes the luminosity. And so now this small star will maintain a stable luminosity and temperature for more than a trillion years as it slowly fuses hydrogen. Now, those same models make predictions about brown dwarfs, how bright they should be when they're born. And so they predict that a brown dwarf with the mass of Jupiter should appear at this location on this diagram. But then after 10 billion years, it would have cooled and faded a great deal down to the lower right corner of this diagram. Because again, brown dwarfs don't fuse hydrogen, and so they never stabilize their luminosity. So they get colder and fainter like a dying ember forever over time. But what this tells us is that if we want to detect brown dwarfs at very small masses, our best bet is to look at places where stars are born. Because it's when a brown dwarf is born that it's most luminous and brightest. And the places where stars are born are nearby clouds of gas and dust called nebula that can contain hundreds or even thousands of stars that have recently been born. So are there any questions so far?
Yeah, can brown dwarfs be found in other galaxies?
So it's almost certain that they do contain other galaxies contain brown dwarfs, but nobody has been able to detect one in another galaxy. And that's because they're intrinsically very faint. And so even seeing them in our own galaxy can be difficult, let alone another galaxy because it's so far away. So any of the questions?
Thank you.
Uh-huh. Okay, so again, the place where we want to search for the least massive brown dwarfs is a nearby nebula of gas and dust that's making new stars, because that's where our brown dwarfs will be youngest and most luminous. Now the next question is, well, in what wavelength range should we search for brown dwarfs? So this is a diagram of wavelength on the horizontal axis, X-rays, UV, optical, infrared, radio. And the vertical axis is the intensity, how bright an object is. And this is the radiation from a star like our sun. So the surface of the sun is about 6,000 Kelvin. So an object with that temperature is brightest at optical wavelengths. A hotter object that's like 60,000 Kelvin, because it's hotter, it'll shine brightest at shorter wavelengths, like the ultraviolet, whereas a cooler object will shine brightest at longer wavelengths, like in the infrared. And so in the case of brown dwarfs, they have temperatures of hundreds of Kelvin, and so they're brightest at infrared wavelengths. So that means we need to use an infrared telescope to search for brown dwarfs. And over the last 30 years, since brown dwarfs were first discovered, I and other astronomers have searched for brown dwarfs in the nearest nebula of young stars. And using infrared telescopes that have been available, we've been able to find brown dwarfs extending down to about 5 times the mass of Jupiter. So that's 5,000th the mass of the sun, 0.005 of the sun. Now, we haven't known whether brown dwarfs existed at even smaller masses because 5 Jupiter masses, that was the lowest mass that could be reached by existing infrared telescopes before Webb. But now Webb is the newest, most powerful, most sensitive infrared telescope. And so it could potentially find brown dwarfs at even smaller masses that are even fainter. And this is a life-size model of the telescope. You can see it's about the size of a tennis court. And this is showing a comparison of the sizes of the mirrors, the primary mirrors on Webb, Hubble, and the previous infrared space telescope called Spitzer. So you can see how the mirror on Webb is much larger than both that of Hubble and Spitzer. And that's important because the larger mirror allows it to collect more light and see fainter things in space. And as we'll see in a moment, a larger mirror enables sharper images in which you can see more detail. So this is an image taken with the Spitzer Space Telescope, this older infrared telescope that was launched about 20 years ago. So this is a Spitzer infrared image of a cluster of newborn stars called IC348. And this is about 1,000 light years away. And that sounds like a large distance, but that's still in our own neighborhood of our galaxy. And this is one of the nearest nebula of young stars. So it makes it one of the best places to search for brown dwarfs. And so the Spitzer image, it was able to see brown dwarfs down to about 10 times the mass of Jupiter, which was quite good at that time 20 years ago. Now, this is showing the area of this cluster that we selected to image with Webb in 2022. So this was the first year after it was launched. So this is zooming in to the old Spitzer image for that central area of the cluster. And this is showing the Webb image. So I'll just flip back and forth so you can see the comparison. So as I mentioned earlier, the bigger mirror on Webb allows sharper images. So you can see how much crisper and sharper the Webb image is. And in addition, because the mirror on Webb is bigger, it can see things that are fainter. And so if you look closely at the Webb image, there are all kinds of faint little things here that you don't see in the Spitzer image. So this was a huge improvement relative to previous infrared telescopes. And all this pink stuff here, all this pink extended light, that's radiation coming from the cloud of gas and dust that surrounds this cluster of young stars. So any questions so far? And so again, those were images we took back in 2022, so 3 years ago, and they turned out to be very successful. We discovered 3 new brown dwarfs, and the faintest one has a mass of about 3 to 4 times the mass of Jupiter. And so that made it the least massive brown dwarf that was known at that time. And so then based on that success, we submitted a new proposal to Webb. And fortunately, it was approved. And in that new proposal, we were able to take images from a much larger area that had much longer exposure times. So we could see fainter brown dwarfs.
Hey, Kevin, before you advance the topic too much further, Mario has his hand up. He has a question, and I think it might have to do with what you're talking about right
Okay,
now.
sure, go ahead.
Well, I didn't mean to interrupt.
Uh-huh,
You
that's
asked
fine.
for this question.
Uh-huh.
So as you discover more and more brown dwarfs, are you noticing statistically there are more of them than red dwarfs, more of them than standard stars like the sun and going upward? Is it following the same numbers as the masses of stars as you go to lower masses? I intuitively would think there would be.
Yeah, that's a great question. So that's a slightly technical question that I wasn't planning to address, but I have the paper presenting these data here, and so I can show you the answer. So this is a diagram of number on the vertical axis. So just the number of stars or brown dwarfs. It's the log of the number. And the horizontal axis is the logarithm of mass. And this is in units of the sun's mass. So 0 that refers to the sun's mass there. And then -1, that would be 10% the mass of the sun. -2 will be 1% the mass of the sun. -3 will be 0.1% the mass of the sun. So that would be the mass of Jupiter. And so this is showing the numbers. So like the least massive stars will be like right around here. They're the most common stars in general. And then you can see the brown dwarfs, they trail off somewhat.
Is that a sampling artifact, or is that real, you think?
Which part?
The fact that the brown dwarfs drop off, I would think
Yep.
that the line would continue to go upward from small stars.
Yeah, that's a great question. So the question is, when you're looking at faint objects down here at the lowest masses, you might wonder, well, maybe some of them are just too faint for you to see. Maybe that's why it drops off. In this case, we think we can reliably see brown dwarfs. We should see all the brown dwarfs in this image down to the last 1 or 2 bins. So above the last 2 bins, that slope we think is real. We don't think we're missing anything.
No.
But then once you get down to the last bin or 2, we might be missing some brown dwarfs that might be just a little bit too faint for us to see.
Okay, thank you.
Uh-huh. So any of the questions?
Are there any brown dwarfs just kind of wandering through space?
Yeah, so what's going to happen is like this cloud, it's like this cloud of gas and dust, this cluster of stars, it's about 5 million years old. So that's quite young for stars. But if you were to come back in 100 million years, most of these stars, they would have just wandered their own way through the galaxy by themselves, like the sun did. Like the sun was probably born in a cluster of maybe 1,000 stars. But then over many millions of years, all those individual stars moved away from each other through their galaxy on their own paths. And so our galaxy is full of individual stars and individual brown dwarfs that are not in clusters. They're just wandering through the galaxy by themselves.
Do they ever evolve with planets?
So do brown dwarfs have planets?
Yeah.
Yep, that's a great question. So the answer is we don't know for sure how common planets are around brown dwarfs. There have been a few planets found around brown dwarfs, but as you might expect, because brown dwarfs are fainter, it's more difficult to search for search for planets around them using all the standard methods that are applied to stars and searching for planets around stars. So the answer is that it's very likely that many brown dwarfs have planets, but that hasn't really been confirmed yet, just because it's kind of hard to find planets around brown dwarfs.
Yeah, thank you.
Uh-huh. So the question is this a Q&A? So no, I'm just stopping for a moment to see if there are any questions. We still have a lot of the presentation left. So any other questions before I move on? So again, we have a new proposal that was approved for deeper images over a wider field. And the goal here is that, in images from 2022, we found 3 new brown dwarfs. That was great, but we want to find more, and we want to find them at lower masses. And so that's why we took images of a bigger area so we can encompass more brown dwarfs. And these images are deeper. We can see things that are fainter at lower masses. And this is the color image from Webb produced for this field. And now this is showing a small little section of that new image, and it's flipping between the new Webb image and the old image from Spitzer. And so this just illustrates once again how much crisper and sharper the Webb image is compared to Spitzer. So you can see far more detail and much fainter things in the new image from Webb. And again, the reason for that is because Webb has a bigger mirror, and bigger mirrors enable sharper images. Now, the name of the camera on Webb that we use to take those images, it's called NearCam. And this is showing the different filters that are available on NearCam. I'm guessing that maybe some of you are familiar with the term filter, but a filter is a device that allows only a certain range of wavelengths to be collected by a camera. And some of these filters are very narrow. They select only a narrow range of wavelengths. Some of them are broader. And now I'm going to show you an example of a spectrum of a brown dwarf. And again, if some of you are not familiar with this term, so spectroscopy is referring to the method of taking light and spread it into its wavelengths into the rainbow. And that rainbow that you see, the light spread into its wavelengths, that's called a spectrum. And that's what this is. So this is intensity or brightness on the vertical axis and wavelength on the horizontal axis. And so this is showing the intensity of a brown dwarf changing with wavelength. And the dips here, where the intensity is lower, where the brown dwarf is fainter, those dips are produced by molecules in the atmosphere of the brown dwarf. So for instance, this brown dwarf has water vapor, it has CO, it has a little bit of methane in its atmosphere, carbon monoxide. But the main point is that this spectrum, it's kind of complicated. There's a lot of structure here. And for me, that's good, because what that means is that brown dwarfs, they'll have very distinctive colors compared to other astronomical objects, like other stars and galaxies. Now, these red and blue lines along the top, that's showing the wavelengths covered by the 6 filters that we selected. Like if I go back here, like one of the filters we selected was this one here, F444. And that's the range of wavelengths covered by that filter. And so the idea is that with these 6 filters, that can give us enough color information that we can separate brown dwarf candidates from other stars and galaxies that we don't care about. Like in other words, like if I go back to this image here, like in this image, there are probably about 10,000 objects that were detected. But only maybe 100 of them are brown dwarfs that are in this cluster. The vast majority of the faint things in this image are just background stars and galaxies that are far, far behind this cluster. And so that's the key, is we need a way of separating the small number of brown dwarfs from all the other faint things in the image. And we can do that with the colors produced by these filters. So any questions so far?
You're saying that brown dwarfs outnumber red dwarfs. How many Jupiter-sized objects outnumber brown dwarfs?
Well, so I showed this diagram earlier. So actually, red dwarfs, they would be these low mass stars here that I'm pointing to. Those are the most common stars. So red dwarfs are actually the most common stars, whereas brown dwarfs are less common by almost a factor of 10, maybe a factor of 5. So in other words, like for another question you could ask is, what are the relative numbers of stars and brown dwarfs? And the answer is that there are about maybe 8 times as many stars as brown dwarfs in the galaxy. But there are 200 billion stars, and so that still means there are probably 30 billion brown dwarfs in the galaxy. So brown dwarfs exist in a pretty decent number, although they're not as common as stars all put together.
Thank you.
So any questions so far? And so this is showing an example of one of the diagrams we used to try to identify brown dwarf candidates. So the vertical axis is showing magnitude in one of the 6 filters that we observed. And the numbers really aren't important. The main point is that brighter things are on the top, fainter things are going to be on the bottom. So faint goes down. And on the horizontal axis, this is showing the difference between the brightnesses in two different filters. And this is a color. So astronomers use the term color to refer to the difference in brightness between two different wavelengths. And so redder goes to the right. So fainter towards the bottom, redder towards the right. And the red line, this shows where we expect brown dwarfs to appear between about 7 and 1 times the mass of Jupiter. So 7 Jupiter mass brown dwarfs are bigger in mass, and so they'll be brighter. And these are some of the data. So some of these things are galaxies. And so the galaxies appear fuzzy in the images that are kind of extended. And so we can throw them away. So it's easy to see a fuzzy galaxy and just ignore it. So now I'm going to remove the galaxies. And then what we can do is we can select all the little dots of light that appear in the vicinity of this diagram where we expect brown dwarfs to appear. So we want to look for ones that are really faint and also very red in this color. And then the next step was to perform spectroscopy on the brown dwarf candidates. So this is showing what's called the focal plane of the Webb telescope. So this is the area in the telescope behind the mirror where images are formed. And this is where all the instruments sit. So there are 4 main instruments in Webb. So the central one near cam, that's the one we use to take the images. And then the one on the left called near spec, that's the spectrograph that we used to perform spectroscopy on the brown dwarf candidates that we identified in the images. And this is showing the layout of near spec, the spectrograph. So all these tiny little rectangles, these are micro shutters. And so what we can do is we can send a command to the telescope and tell it to open the micro shutters that will be right on top of the brown dwarf candidates. And so by opening the micro shutter that is over a brown dwarf candidate, that allows us to take a spectrum of that brown dwarf candidate. And so because there are a few 100,000 micro shutters, we can open maybe like 5 or 10 of them that are right on top of brown dwarf candidates for which we want spectra. And so then we did that. So we used this instrument to get spectroscopy for the brown dwarf candidates. And we ended up finding 9 additional ones beyond the 3 that we found in 2022. So here's this diagram that I showed you earlier of luminosity versus temperature. And so it turns out that astronomers, they use a letter to abbreviate temperatures. These are called speckle classes or speckle types. Maybe a few of you have heard of them before. And so, for instance, these are the letters, the speckle classes that apply to cool stars and brown dwarfs. So M, L, T, and Y. So in other words, astronomers, they use these letters as a shorthand or an abbreviation for temperature. And these letters are defined based on the molecules that appear in these different temperature ranges. So for instance, methane, CH4, T dwarfs are defined by the presence of methane. Now, if you go to even colder temperatures, ammonia appears, NH3, and that defines the Y class. So these different letters, these different classes, they're defined by the presence of different molecules. So how is that relevant to what I'm talking about here? So on the top, this shows an example of an L-class brown dwarf that we found in this cluster with Webb. And so we've seen many examples of these L-class brown dwarfs in the past. But in addition, we found other brown dwarfs that have a hydrocarbon feature that has not been seen previously outside the solar system. So previously, it had only been seen in Saturn and Titan that are atmospheres. And so because we discovered this new hydrocarbon and several of these brown dwarfs, we proposed a new class of brown dwarfs called H-class brown dwarfs, where the H stands for hydrocarbon. So any questions so far? And so, as I mentioned, we found about a dozen brown dwarfs between the data from 22 and last year. And the faintest of them are shown here. So these are the four faintest. They all have mass estimates of only about 2 times mass of Jupiter. So that makes them new record holders for the least massive known brown dwarfs. And so it's pretty amazing that the process that makes stars is able to make objects extending all the way down to only twice the mass of Jupiter, which is again about 500 times smaller in mass than the sun. Now, we don't know whether brown dwarfs exist at even smaller masses. To answer that question, we need even deeper images with longer exposure times that can see even fainter brown dwarfs at even smaller masses. And that's something I'm hoping to do over the next few years, if I can get more time with the Webb. So any questions so far?
I have a question. Does the math indicate that there might be brown dwarfs smaller than 2 Jupiter masses and we just haven't found them?
Yeah, it's a good question. So there are different theories for how stars and brown dwarfs are born, different simulations, and different theories, different simulations, they make different predictions for what the smallest mass should be. So some theories predict that the smallest brown dwarfs should be maybe 20 times the mass of Jupiter. But other theories say that, oh, no, we can make brown dwarfs down to the mass of Jupiter. And so there's a wide range of minimum masses that are predicted by different theories for how stars and brown dwarfs are born. But 2 Jupiter masses, that's already pushing it. That's pretty difficult for almost any theory to explain. And if we were able to find brown dwarfs down to the mass of Jupiter or below, that would be a really big challenge for any theory to explain. I mean, we can explain planets forming at those small masses, but not things that form like the sun. It's really hard to explain how something that forms like the sun could be born at such a small mass.
Thanks.
But that's not my problem. I just find them, it's the job of the theorist to explain them. So any of the questions?
Did you mention surface temperature on a brown dwarf?
Or so are you asking what would the surface temperature be for these brown dwarfs?
Yeah,
Yeah, so like for the 2 Jupiter mass ones here, their surface temperatures might be 800 Kelvin, maybe 1,000 Kelvin, something in that ballpark. So that's a lot warmer than Jupiter. And the reason that they're relatively warm is because they're young. So remember I showed you the diagram earlier of brown dwarfs getting colder and fainter over time. So because these brown dwarfs are newborn, very young, they're still relatively warm, even though their masses are so small.
they can't be burning or heating themselves very hard, considering they haven't got much mass.
Yeah. So I mean, they don't have fusion. They don't have a source of energy. The heat they do have is the heat that's left over from when the original cloud collapsed. And that gravitational energy was converted into heat. So they still have their heat of formation left over.
And that just deteriorates.
It just gets colder and fainter over billions of years. Yeah. So any of the questions? So this is again the original Webb image from 3 years ago for the center of the cluster. So it turns out that some member of the public, I don't know who, but they submitted this image to the post office to put on a stamp. I didn't know this beforehand, but it turns out that the post office has a website where members of the public can submit suggestions for new images to appear on stamps. And so somebody submitted this image to the post office, and the post office selected it late last year, and it was published on the highest denomination of stamp, the Priority Mail Express. It came out in January. So these are expensive stamps. They're like $31. But that was an unexpected, neat result of all this. So one thing I want to point out here is that, again, many of you may know this already, that just because an astronomical image is visually striking and pretty doesn't mean it's scientifically important. And in the same way, there are lots of kinds of data that astronomers take that don't make pretty pictures, but that are very important scientifically. So those are not necessarily the same thing, a pretty picture and something that's important in science. And a good example is the image I'm showing you here. So like this image is very pretty, very visually striking, but all the pretty stuff you see here, this pink extended light, it's actually a big nuisance for me because it makes it more difficult for me to see the faint little dots that correspond to brown dwarfs. So sometimes the pretty aspect of the image is actually bad. It's a nuisance. Whereas there are other times where there's a direct connection between what's visually striking and what's scientifically important. So for instance, this is a Hubble image of the Whirlpool galaxy. It's a very nice, striking image. So in this case, the image is visually striking because of the very high resolution, which allows you to see a great deal of structure and detail in the galaxy. And that detail and structure is also very good scientifically in terms of studying the galaxy. So here, what's pretty is also important. But that's not the case in this image. So like if I could, I would prefer just to take away all this diffuse light so that I can more easily see all the brown dwarfs by themselves. But I can't do that because I'm looking for brown dwarfs in clusters of newborn stars, and those clusters of newborn stars are always in nebula that have this kind of extended light. So it's something that's kind of unavoidable for me. So any questions so far?
I was going to ask one, but I think you've already answered it. I was going to say, if you just use a mid-infrared filter, a far infrared filter, wouldn't that enhance the brown dwarfs and de-enhance the nebula?
Yeah, so unfortunately, this extended emission, it's basically present at all infrared wavelengths. There's no wavelength at which you can avoid it. I mean, there are some wavelengths where it's brighter, some where it's a bit fainter, but it's always going to be there at some level. So any of the questions? So here are a few more additional results from this work. So it turns out that so most of the brown dwarfs we found were just by themselves in the nebula. They weren't orbiting anything as far as we could see, but there were two examples of two new binary brown dwarf systems that we found in the nebula. And so this is an artist's rendition of a disk of gas and dust around a newborn star. And so it turns out we found evidence of one of these disks around one of the two Jupiter-mass brown dwarfs. So this is a little bit technical, but so these disks, they have a lot of dust, and the dust tends to be cool. And that cool dust will produce a lot of extra infrared radiation at the longest infrared wavelengths. And that's illustrated here. So here, the red spectrum is the normal brown dwarf that has no disk. The black one has a disk. And the reason we know it has a disk is that it's brighter at longer wavelengths. It has extra emission due to the dust in the disk around it. And so the fact that the black spectrum has this extra emission, that tells us that it has a disk of gas and dust around it. And that's important because it's these disks that produce planets. And so if this true Jupiter mass brown dwarf has a disk of gas and dust around it, that means it could potentially one day have a planetary system. And so you can imagine a true Jupiter mass brown dwarf with its own tiny little planetary system around it. So you can think of it as like a miniature solar system. And so that's another exciting aspect of this. And this is the least massive brown dwarf for which we've found evidence of one of these disks around it. So that's the end of all the slides I had planned. Any questions?
Brown dwarfs must form out of the same clouds that stars are forming. How often do you get binary formations where the brown dwarf is flung into space after a period?
So do you mean a brown dwarf is born orbiting a star and then
Yeah.
it gets ejected?
Yeah.
That's a great question. We don't know. We don't know how often that happens. Astronomers, they can run simulations of that sort of thing, and they can maybe make a guess for how often it happens, but we don't actually know.
Kind of opens up a whole new field of objects and reasons that they're moving, and you don't even know they're there.
Yeah. So actually, the question I thought you were going to ask is that when you start talking about binaries, is that I thought you were going to ask how common are binary brown dwarfs?
That's another good one.
Yeah. So it turns out that like stars like the sun, maybe about 50% of them are in binary systems. But as you go to smaller stars, binary systems become more rare. Like in the case of brown dwarfs, maybe about 15 or 20% of them are in binary systems.
What I find fascinating is like when we got to Pluto, we finally realized, hey, this has got more orbiting objects than we thought in the first place. It's got to be the same thing with brown dwarfs and other stars that we're only seeing the tip of what could be a galactic iceberg.
Yeah, there are always smaller and smaller things orbiting smaller bodies. So like all the, I mean, pretty much all brown dwarfs probably have some sort of little bodies orbiting them to some degree. There's a question in the chat window. So what temperatures could the planets have? So the temperatures will probably be pretty low because since the brown dwarfs lack fusion, they're quite faint and cool. And so there would be very little heat received by any planets surrounding a brown dwarf. Beyond that, the exact temperature of a planet around a brown dwarf, it would depend on how close it is to the brown dwarf. So if a planet's closer to the brown dwarf, it'll be somewhat warmer. If it's farther away, it'll be somewhat colder.
Is it true they found a planetary system around 3 bound brown dwarfs where the planet is has an unusual orbital pattern? It's called 3M1510. 2M.
I'm sorry, go ahead. So, I mean, that rings a bell. I think maybe I saw a headline about that, but I'm not familiar with a particular study. So I don't remember exactly what that involved. Now, so one question that people often ask, and I have a later slide for this, is so what's the distinction between a brown dwarf and a planet? And so the answer that I would give, and I think and so first of all, so the answer to this question is sort of controversial. You'll get a different answer from different people. But I think the most common answer from astronomers is that we define the distinction between brown dwarfs and planets based on how they're born, where a brown dwarf is an object that doesn't fuse hydrogen, and it was born like a star. It was born from a cloud of gas and dust collapsing. And that's illustrated like on the bottom. This is supposed to represent a cloud collapsing to make a star, and on the top is a smaller cloud collapsing to make a brown dwarf. So a brown dwarf forms like a star, just on a smaller scale. Whereas a planet is a small body forming within a disk of gas and dust that surrounds either a star or a brown dwarf. So I would define the distinction between a star and a planet based on the mechanism of their formation. A brown dwarf forms like a star. A planet forms in a disk around either a star or a brown dwarf.
Could brown dwarf gravity do the same thing to orbiting objects that Jupiter does to Io, where it creates heat at a distance that way with gravity?
Yeah, so you're referring to tidal forces. Yeah, so any central body can exert tidal forces on a smaller orbiting body. So they could be a satellite orbiting a planet or a planet orbiting a brown dwarf. Yeah, so it all depends on the distance. So if the distance is small enough, you can have those tidal forces become significant.
Thanks.
Uh-huh. And so in theory, you know, I mean, like when people sometimes talk about the possibility of life on a planet around a brown dwarf. But the big problem is that the central body is getting colder and fainter over time. And so, you know, it might be difficult for a planet around a brown dwarf to maintain the right temperature to have liquid water, for instance. But in theory, if you have tidal forces from the brown dwarf, that might help to heat up the planet enough that maybe it could still have water in liquid form, either on the surface or maybe below the surface, like on Europa, for instance, around Jupiter.
Yeah, it opens up a lot more potential.
Uh-huh. I mean, I think the main thing to take away on that front is that there's probably a huge diversity of planets in the galaxy with all kinds of central bodies ranging from 2 supermass brown dwarfs up to stars that are much more massive than the sun. So any of the questions?
You got a quiet audience.
Uh-huh.
Kevin,
Uh-huh.
I know we saw a chart with a couple of molecules that were in each class of brown dwarf.
Uh-huh.
But surely there are other things involved other than water and ammonia. And I was wondering if the makeup of the cloud had been mapped in other ways against things like luminosity.
Are you asking, are there additional molecules in addition to the ones shown here in brown dwarfs, or?
That differentiate them by luminosity, yeah.
I mean, there are additional molecules in smaller abundances, like CO2, for instance, carbon dioxide. But the ones shown here, those are they're dominant by far. These are the most abundant molecules in the atmospheres of brown dwarfs.
Oh, okay. All right, terrific. Well, if there's no other questions, I'm going to say thank you very much, Kevin. This is really a terrific talk.
Sure. Well, thanks for all the great questions.
Yeah.
Thank
great
you very much.
presentation. Thank
Excellent.
you.
Let me just check the chat. There were. Well, we don't need that. Okay. All right. Well, then, good night, folks. Good night, Kevin. Thank you again. It was really
Thank you
good.
very much, Mike.
Unexpected
Thank you,
information. It's
Nice
terrific.
job, Mario, with the photo of the sun, Mario.
Thanks, Kevin. I have that same toaster, by the way.
All right. Uh-huh.
The red toaster.
Interestingly, I have a photo of IC 348, which I took with my 0.8 meter.
Uh-huh. That's great.
It has some of that same structure. So I'm not sure, Bill is the expert and Kevin, you're the expert, but are those shock fronts for those lines?
You mean the extended light you see in the image?
Yeah.
veil.
It's scattered starlight. So it's light from the central brightest stars that's reflecting and scattering off of
Yeah, but it seems to have like lines, I
Uh-huh.
realize it can't be that many
Have
shock
an
fronts.
angel there.
It seems to have
you mean the
some kind
structure?
of structure, which is interesting. I don't understand it. Could
I
it
mean,
be magnetic field lines organized in the
Um,
gas?
I mean, possible. I would guess that a lot of this is due to the winds of the stars, especially the most massive ones. So those winds can be quite strong and they can push away some of the nebula. Um, when stars are born, they also have outflows. Like if we go to, um, where's that image? It's a little bit hard to see. So like here down the right-hand corner, this is a huge outflow where material is being shot out from a young star in two different directions. And so we think these outflows happen for all stars that are born, newborn at some point. So those outflows can also push the gas and dust around in these clouds.
Hey, Kevin, when a brown dwarf gets to be very cold or loses all of its heat, what does it become in terms of, is it a gas? Is it a frozen hydrogen ball? Is it semi-solid? What does it become?
Well, so it would never, I mean, on the time scale of the age of the universe, it wouldn't become, no, there's no brown dwarf that would lose its heat. It'll just get slowly colder and fainter, but never really coming very close to absolute zero, for instance. But if you wait long enough, like many, many trillions of years, it'll be cold enough that it'll start to become kind of like a white dwarf, in that it'll be a big ball of degenerate matter. So a very, very dense form of matter.
So it would get hotter,
It wouldn't get hotter. It's the density would get somewhat higher. Um,
but it's
because-
never going to be a hydrogen snowball. Because I thought once it gets down to about minus, I don't know, 200 and something centigrade, hydrogen's going to freeze up.
That's right. So I mean, it is mostly hydrogen. That's right, and that's going to stay that way, that composition. But to get to that temperature you're referring to, I mean, you would have to wait some kind of, I don't know, like 10 of the 20 years or something crazy, crazy long time to reach that temperature. In other words, like there's no brown dwarf that's come anywhere close to that cold of a temperature in the current age of the universe.
Wow.
But that's something you can predict. I mean, there are astronomers who could predict exactly how long you'd have to wait for a brown dwarf to reach a certain temperature and become an extremely dense, degenerate object like that.
Does Jupiter radiate more heat than it gets? I thought Saturn did.
Well, so I mean, so none of the planets have fusion, so they don't have their own source of energy.
No, but they absorb from the sun.
Right, that's right.
Well-
But they are receiving sunlight, and that keeps them at a stable temperature. Whereas if the sun was absent, they would be a lot colder than they are.
So Jupiter doesn't get hotter towards the middle.
Yeah, I mean, yeah, so the deeper you go into any object, it's going to be hotter. The same thing for a brown dwarf or a planet or a star. So as you go deeper and deeper towards the center, there's more and more pressure, and therefore the temperature is higher and higher. So it's always hottest at the center and coolest at the surface.
Sure. Okay. Thanks.
Uh-huh.
Think that's it, Michael.
All right,
Okay.
I'll try one more time.
Have a great
Are
night.
we ready to go, or is there another question out there? What's that, Tom?
It's talking about how cold it has to be for hydrogen to go dense phase.
Yeah, I didn't know that. That's not, I didn't know that. It's good to know.
All right, that's enough silence.
Thanks,
Good night,
everybody.
everybody.
Good
Thank
night.
you.
Thank
Good
you,
Thank
Richard
you.
and Kevin.
Thanks, Kevin.
Bye-bye. Thanks.
You're getting a lot of comments.
Good night.
Happy birthday, Michael.
Thank you.
Happy birthday to you.